So the way we're going to do that, I love these eyes. We develop these things called Snoopy caches. Right? So a Snoopy cache is a pretty sophisticated cache. It does everything a normal cache does, but it also watches the bus to see if there's any transactions involving memory locations that it happens to have a copy of. So in this case, when program 1 goes off and changes the value of x in the cache, and then we do a transaction to change that value off in memory, change this guy, this bus transaction is visible to this other cache. It can say, oh, I notice you're changing the value of a variable that I'm caching. I'll update my value in my cache. Okay, so these Snoopy caches were quite, everybody said, oh, this really does solve the problem. Now we actually are back into the sequential consistency game, right? There's none of these notions now that it depends which order we do things in, right? If we're printing x before or after it changes, that'll determine what we print out. But at least we have a situation where if the value of x changes, everybody in the whole system now agrees that the value of x has changed. There isn't a notion of you think it's 1 and I think it's 3. At some point here when I change it to 3, this Snoopy cache arranged for everybody now to think that it's 3. Everybody sort of get the idea there? So we have this sort of notion that everybody agrees, at a particular instant in time, everybody agrees what the value of a variable is. In clock cycle 12, and thereafter the value of x is now 3. So this notion of being able, when I do a transaction, to update the values, or perhaps the cache will say, I haven't looked at the value of x in a while. You're obviously starting to change it over there in process 1. Why don't I just get rid of it in my cache? So the Snoopy caches have a notion that they can either keep updating their value or they can just invalidate the value. Say, look, I'm forgetting all about x. I'm no longer interested in the value of x. Okay. So Snoopy caches are sort of neat. And in fact, we can do better about having to do a write-through cache. And I don't mean to belabor this table too much, but I'm going to spend a second here because it's sort of fun to think about a little bit. So suppose nobody has read anything. And the first time I read, for instance, the value of x, I want to manipulate the value of x. What I discover is that, look, I'm in this column, and it's invalid in my cache, so I'm going to go to memory. So I, as the first person to read x, go to memory, read x. I now have it. And since this notion, I didn't hear from any of the other caches, they all reported that they didn't have a copy of x. So every time I fetch something, the other caches are reporting to me if they have a copy. I don't really care who has a copy. I just want to know if there's another copy out there. So the notion of not only missing in my cache, but the snoop miss means I missed in all the other caches. All the other caches says, I don't got it. Now I know I have exclusive use. Now whenever I change that variable, do I have to do anything in order for everybody to agree on what the value of the variable is? No, I'm the only one who's got a copy of it. So I can write it. I don't have to do write through. I don't have to do anything expensive. I can just pound away on it in my cache and no one cares. Now what happens when you read the value of x? So it missed in your cache, but I say, psst, by the way, I have a copy in my cache. So when I see your bus transaction to fetch the value of x, I probably will supply my updated value of x. Instead of the main memory, I say, I have the most recent value because I changed it. It went from exclusive to modified when I wrote it. Since I have a modified copy, I'll give you my copy, and we'll all mark it as being shared. So now the caches understand that for particular variables, more than one person is interested in the value. More than one other cache is interested in the value. And every time with a shared location, any time that value is now changed, okay, I have to tell you all. I have to say, psst, the new value is x. So we're implementing the strategy that I described on the previous slide, where everybody gets to see all the changes. We're just keeping track of, if there's no one else who's interested in the changes, I don't have to go to all the expense and power and time in order to let everybody know. I only have to let you know if we're actually discovering that we're sharing a variable. So this fancy MESI protocol, Modified Exclusive Shared and Invalid Protocol, was a pretty neat idea. It works well when you have a handful of processors, 2 processors or 4 processors. It doesn't work well with 1,000 processors. Okay, because there's just too much communication that happens there. Okay, but for a small number of processors, we actually were able to come back and get sequential consistency. Now we could have a notion, or we could have a very clear semantics of what it meant to run a program in parallel on multiple processors, accessing shared memory locations.